Hello dears, this is the first week of module 2. The delivery plan of this module will be as follows. In week number 4, we are going to cover the modeling of translational mechanical system. Then week number 5, modeling of rotational mechanical system. And finally, week number 6 will be modeling of rotational mechanical and electromechanical system. So here we will start the translational mechanical system transfer function. The mechanical motion can be either translational or rotational or a combination of rotation and translational. The translational mechanical system will take place if the motion is going in a straight line or curve. So either it's a straight line, as you see here, this is a straight line, or it's in a curved way. In both ways, we call it a translational mechanical system. In a translational mechanical system, the input is force, with the output is displacement. There are three elements used to make the model of mechanical system. Means any mechanical system can be expressed with these three elements. They are, as seen here, spring, mass, and damper. Spring, mass, and damper, where the spring and the mass are energy storage elements, with the damper is dissipated energy. They are analogy of electrical system, where the spring and mass similar to the capacitor and inductor, and the damper is similar somehow to the resistor. The three elements are shown in this table with their expression in Laplace format. So here is the spring, damper, and mass, where the spring in Laplace expressed as a K, where K is the constant of the spring. Damper is expressed as a FVS, where FV is the constant of the damper, and ms square is the Laplace expression of mass, where m is the constant of the mass. The units for these elements are given here, where in the spring, its unit, its constant is K, as I mentioned in the previous slide, and its unit is in Newton meter. And the damper, its constant is FV, with a unit of a Newton second per meter, and the mass, its unit is kilogram. Mainly, Newton's law is used to develop the transfer function of mechanical system. The statement of Newton's law is saying the total forces acting on a body is equal to the acceleration multiplied into the mass. Or mathematically, as seen here, you will find it's the summation of forces equal to the mass multiplied into the acceleration. We are going to follow few steps to get the transfer function done. The steps are given here, and we will see them in the coming example after a while. Step number 1, it's to draw the free body of the system you want to find its transfer function. Then after that, we will write the differential equation by the help of Newton's law. Then we will assume initial condition when we find the Laplace transform of the system, and after that we will obtain the transfer function. Here is a translational mechanical system, where in this translational mechanical system we have the component mass, damper, and spring, with a force Ft applied and the force causing displacement to m. The displacement is xt. So the input of the system is Ft, where the output is xt. So what is the transfer function required? It's the output over the input, but in Laplace. So it's going to be xs over fs. Let us develop the transfer function step after the other. So in step number 1, we are going to draw the free body diagram. What is the meaning of the free body diagram? We are going to put the mass, as you see here. We will put the mass, and we will check the forces applied to that mass with the input and output. So we will find here that there is a force Ft applied to this direction, and opposite forces will be developed by the three different elements. One of them is K, the other is Fv into dx by dt, and the third one is m into d square x by dt. Now, out of this, we are going to write the differential equation. Differential equation is saying the total forces in general, I can say total force is equal to 0. So we will look at them as the force caused by the mass, which actually it's a force resisting the force applied. That means it's in the other direction. That's why I'm saying resisting, because it will be in opposite direction. And then the one due to the damper, which in opposite direction, plus the one due to the spring, which in opposite direction, is equal to the main force. This is the differential equation which is describing the system, and we call it the equation of motion. We will put it in Laplace, then we will develop the transfer function. Let us see this in the next slide. So here we will assume initial condition when we find the Laplace, when we put the system in Laplace. Putting the system in Laplace without going to very much complexity, because in the table given a few slides ago, in the table given, each of the mechanical element has its Laplace equivalent. Like for example, the spring, in Laplace we express it as a k into x of s. The damper is Fv into s into x of s. The mass is ms squared into x of s. The force is f of s, and x is x of s. So we will rearrange it or write it in a form of equation. Or you can think of it as converting the differential equation given in the previous slide to be this equation. So if I convert it, it's going to give us this equation in Laplace. Let us take xs common. X common from all of them. The equation going to look like ms squared plus fvs plus k into xs, which equal to fs. Rearrange the equation in step number 4. Rearrange the equation to put it as output over input. That means xs over fs, as you see here, is going to result in this value, where this value is the transfer function representing the system. To remind you, the meaning of transfer function means it's the mathematical expression describing the system for control system application, where the input will be the force and the output will be the displacement. Important observations will help us in dealing with the coming system after a while. It's going to simplify the coming system. So Zm is equal to f over x. Then we can write it as f equal to Zm of s into x of s. In this case, we can compare this equation as an analogous of the electrical system. So we can say this is similar to V equal to Zi. Why we are getting this one, or what is the important notice we want to get here? We are going to treat the mechanical elements as impedances. We will call them mechanical impedances, as you see here. So the impedance is equal to F over X. Any of the impedance is equal to F, which is the force, over the displacement. Similar to the electrical system, the impedance is equal to V over I. Here, the mechanical impedance is F over X. So in this case, when you compare or when you look at the equation developed earlier, you will find it's nothing but the sum of impedances x of s into x of s is equal to the sum of the applied forces. So without going to the steps mentioned earlier, we can directly develop the equation considering this idea. Translational mechanical system with 2 degrees of freedom. The degree of freedom is equal to the number of independent displacement caused by the force applied. So if there are 2 displacements, means the system considered as a 2 degree of freedom. Now, how am I going to get that degree of freedom? We will see it in the next example and on the system shown on the example of the next slide. The number of equation for a system which having more than 1 degree of freedom, the number of equation is equal to the degree of freedom. Means if the system is 2 degree of freedom, 2 equations are required to describe it. If the system is a 3 degrees of freedom, 3 equations are required to describe it. To develop the transfer function, we are going to apply whatever discussed in the previous example, but we will take each mass by itself in separate, and we will apply the superposition technique.